Hi, everybody. Welcome to another episode of Read Science, where myself, Joanne Manister, Science Goddess on Twitter and a blogger at Scientific American, joins my co-host, Jeff Schomeyer, who is Scienticity on Twitter. And we meet to speak with popular science authors about why and how they write their books and create them so that they are engaging and understandable to the general public. And I'm going to turn it over to Jeff to introduce today's guest.
Our guest today is Chad Orzel, author of How to Teach Physics to Your Dog and How to Teach Relativity to Your Dog, both of which Kirkus reviews apparently think of as quirky science primers. But I should point out that quirky is one of my favorite adjectives, so that's good with me. His co-author on these books is a German Shepherd mix named Emmy, who apparently has frequent inspirations for not quite practical ways to apply quantum mechanics and relativity to the problems of chasing bunnies and squirrels. Chad is a native New Yorker. He got his PhD in chemical physics from the University of Maryland, College Park, a place where I coincidentally worked for 12 years, several of them while he was there, it appears. We both fit into that very broad category known as condensed matter physicists. Chad is currently an associate professor in the Department of Physics and Astronomy at Union College in Schenectady, New York, where he teaches physics mostly to humans. His blog is Uncertain Principles, where it seems he promised he would have something to say today right here in his dog voice. So today we're here to talk about the connections between quantum mechanics, relativity, and bunnies. Welcome, Chad. Thanks for joining us.
Oh, thank you for having me. Emmy isn't able to join us because we're doing this from my glamorous office on campus. I do have a very small picture of her back here, just so she's here in spirit.
That's great. After I ask the first question, I'm going to go turn off fans, which I believe are making me keep cycling in and out as the main person on your screen, which shouldn't be happening, but I think that's what's going on. I have 4 kids, and my 2 oldest are in the hard sciences. And their dad also was in the hard sciences. And they're very good students, all of them. And they've taken physics and calculus and differential equations. But all of them seem to struggle when they hit that semester for the quantum physics that they're required to take. Now, I didn't have to. I'm a biologist, so I took something above physics for poets but below physics for physics majors, right? So why is it that even excellent, intelligent people struggle with quantum mechanics? And in answering that, I guess you'll be answering why you wrote the books that you did.
Yeah, the issue really is that quantum physics is very unlike everyday physics. We have fairly good intuition for Newtonian sorts of problems, things on an everyday scale. So if you're talking about a baseball or a basketball or the World Cup's going on, so a soccer ball. That sort of thing behaves in a way that we see on a regular basis, and you understand more or less what's going to happen with those objects. Quantum things, on the other hand, behave according to very different rules. So particles behave like waves, both particles and waves at the same time, and that's a very strange sort of situation. You have something like an electron that isn't easily localized to one point in space, but sort of naturally is spread out over a wide region, and that's very counter to our intuition. So the thing that works really nicely about the dog as a vehicle for this is that dogs approach the world in a very different way than people do. So part of the idea of the books is if you can look at the world the way a dog does, as sort of an endless source of surprise and wonder, then a lot of these quantum things are easier to approach. If dog treats suddenly materialized out of nowhere in the middle of my kitchen, I would be a little freaked out by that. That would be kind of weird. But my dog has been waiting for that to happen for years, and so she would just feel vindicated. And so the notion of something like a virtual particle in quantum mechanics that just pops out of nothing and then disappears again very quickly. That's something that's, if you think about it from a different angle, from a sort of canine slant, becomes a little easier to deal with.
That's actually a pretty funny way to go ahead and approach that. That, like, yeah, we would be surprised by that, but dogs are thinking about things a little differently. So maybe the quantum realm is a little more transparent to those of us who don't think too hard. So yeah, go ahead, Jeff.
I was just going to say, do you think that the wave-particle duality issue is the central impediment to understanding that, or I don't know, sort of a? I want, is it? There's so much. It's clear that the small world works a lot differently from the big world, and maybe we just don't understand very well right now about it. Maybe we never will, but all of those, what's the core impediment?
Well, I think the particle wave question ends up being central to everything, because you can understand all of the weird stuff that happens in quantum mechanics as coming from the fact that you need to have both particle and wave properties at the same time. Right? Things like electrons are unquestionably particle-like in that when you detect one, you'll find it at a single position at a single time. But they also have wave nature, as you can do experiments with diffraction of electrons or sending them through two slits at the same time, and you'll see an interference pattern that's characteristic of wave behavior if you do that experiment over and over and over again. And having those two sets of contradictory things together is what really requires a lot of the weirdness of quantum mechanics.
And so, I like the way you worked out some of those implications. Particles over here, you can count them, they're there. Waves, they're not in a particular place, and they don't have numbers. You can't count them.
Exactly. Yeah. So a wave is a disturbance that's sort of spread out over a wide region of space, where a particle is a thing that's at a particular position, and those are very different things. If you want a little of each, you have to sort of mix them together, and that leads very directly to things like the uncertainty principle and things like Schrodinger's cat physics, the idea that objects can be in multiple states at the same time, which is very disturbing to someone with working from classical intuition, but it's essential, and it comes from the wave-particle thing in one way of looking at quantum physics, anyway.
I had one place where I was going to say, we talk about quantum mechanics, and we talk about the randomness that's inherent in it, and you made the point, which I thought was important there, that the randomness is controlled. Things aren't just wildly random, and it's not because the experiments are bad that we don't know that there's an indeterminism of what's going to happen, that it's a fundamental thing, but it's not a free-for-all either. It's not quite the anything can happen thing that some people like to imagine.
Yeah, I mean, there's a sense that anything can happen, but many of the things that can happen are fantastically unlikely and are just never going to show up. But it is true. There is an element of randomness to it, and there's an important distinction to be made between the randomness that shows up in things like the uncertainty principle in quantum mechanics, which is really a fundamental limit on what we can know about a system, versus the randomness that shows up in classical experiments, where we do these experiments in our intro labs with projectile launchers. And you fire a little plastic ball across the room. It's not going to land in exactly the same spot every time, because there's air currents in the room. There's the ball rolls a little differently as it comes out of the launcher each time. You get a little bit of variability because of things that you don't measure. And that's not necessarily what's going on when you think about the fundamental quantum randomness. Is really a matter of things not having properties that we would expect them to have in a classical sense.
So I was wondering, I was charmed throughout the book because you had to take a very different voice to do this, because you have a dog speaking. You're talking to the dog. Dog's talking to you. And in How to Teach Relativity to Your Dog, for instance, Emmy is bolting around the yard along the fence because she wants some bunnies. And you use this opportunity to discuss contraction in this relative sense. So why don't you discuss how you build a discussion with a dog to teach this? I mean, the best way to appreciate this is to read this, actually, for those of you watching.
I think this is in the nature of an invitation.
Yeah. So I was just saying the origin of the books is, I mean, anybody who has a dog talks to their dog, and I actually do carry on conversations with the dog, and I'll do her half of the conversation in a silly voice. Because it makes my wife laugh. And this started off with just the dog gets kind of it's like an Andy Kaufman foreign guy voice. It's, I like cheese, sort of thing. And so I started doing the silly voice for the dog, and then it gets a little harder to make her laugh, and so physics things started to creep into that. And then one day I was in a silly mood. I wrote a conversation, this blog post that was an imaginary conversation with a dog about quantum electrodynamics, where the dog is saying that bunnies made of cheese are appearing in the backyard and disappearing because of QED as virtual particles. And I explained that no. A bunny made of cheese would only last 10 to the minus 40 something seconds, and things like that. Just because I was in a weird mood, and people seemed to like that, so I did it again. The second time I did it, I talked about the many worlds interpretation of quantum mechanics. Boing Boing linked to it, and 50,000 people read this silly conversation. One of whom was an agent who contacted me and said, this would be a great idea for a book, and my initial reaction was, really? But after thinking about it and talking to some people, I was like, yeah, this actually works pretty well. And so I wrote up a proposal and sold the quantum book. The dog stuff is the most fun part to do because a lot of the things that are in there, the bunnies made of cheese thing is was just tons of fun to write because having the dog's point of view of things, and it's always she has some angle on getting treats or catching rabbits or catching squirrels, and she's always got some angle on it, and it's really fun to come up with the dog's half of those conversations, and what she's going to be pushing for, and that flows really easily. What ends up being really hard is writing the straight explanation of the physics behind it. That ends up being a ton of work to go into. Even stuff that I know very well from doing research on quantum physics and things like that ends up being it's hard to explain at a reasonable level. But that's the other device that's in there is every now and then through the text of the book, the dog interrupts as if she's reading the manuscript over my shoulder and says, no, you're not doing that right. And then I explain, okay, what's your problem with this? And so break that up a little bit. So it ends up being a really nice device to, there's some pretty heavy physics in both of the books. Goes into some detail about things that you don't often see in popular treatments. And I think what enabled me to do that was having that, whenever things start to get really heavy, then I can have the dog break in and say something. There are a couple of places where the dog interjection is just purely because we need something silly right here, or else people's heads are going to explode. Once we get the little brief interlude, then we can move on to the next thing.
So
it is a lot of stuff, yeah.
It is. Would it be okay?
It's the equivalent of the Raymond Chandler line about whenever you get stuck, just have somebody break through the door with a gun, in your mystery story. It just, whenever it gets like, oh God, this is hard, then have the dog say something.
So would it be okay if I read a little bit from this chapter where Emmy is trying to shrink the bunnies?
Sure.
I won't sound like you or your dog. I'm not that good. So this is chapter 4 in How to Teach Relativity to Your Dog. And it's Honey, I Shrank the Bunnies, length contraction. And it says, Emmy's patrolling the backyard, and when I head out to see what she's up to, she explodes off the patio and runs in a huge circle to the back of the yard, then back close to the house and along the neighbor's fence. She pulls up short at the fence, then takes off again, even faster for a second pass, and we've all seen our dogs do this. What in the world are you doing, I ask. She skids to a halt at my feet, panting. I figured out how to make it through the fence, she says. I'm going to squeeze through the gaps and get those bunnies in the next yard. I don't think you're going to make it through those bars, I say. You're significantly wider than the spacing between the bars of the fence. That's because I'm standing still, she says cheerfully. Once I get fast enough, I'll fit, because of physics. This is another relatively based scheme, isn't it? I sigh. All right, what's the latest brilliant plan? Well, according to relativity, moving objects shrink, right? So if I go fast enough, I'll be small enough to fit through the bars. Now, I'll stop there, but I think this gives people an idea of the kind of conversation they will encounter in the book. It's really casual. It's actually really lively. And we know, that a dog's doing this. And, it goes on that, of course, you explain, well, if you run enough, you'll get skinny, but you still won't fit. But she's talking about that length contraction, like from her nose to her tail, and then you go into the whole relativity of, things are relatives, but then the fence,
right. Yeah, what she would see, she wouldn't see herself get smaller. She would see actually the fence get smaller, which is the really strange thing about relativity that gets people twisted around. Is that you think of moving objects get smaller, but the really interesting thing about it is you can't define an absolute standard for what is a moving object that gets smaller. So both parties will see in some exchange will see the other one appear to get smaller. So if I'm standing in the yard watching her run at, assuming she could actually run at close to the speed of light, I would see the dog shrink nose to tail, but what she would see is the slats of the fence get closer together, and so it would actually do her absolutely no good at all. And then I explained that to her, and then she says like, well,
so there's a lot of almost get it, but not quite.
Yeah, there are a lot of schemes that she comes up with that almost work if you do it a little bit wrong, and then I explain how it actually works.
Well, she had a similar scheme in the quantum mechanics book for diffracting through the picket fence to get the bunnies. And so,
right, she was going to diffract through the fence, or at one point she was going to go around both sides of the pond in the backyard and trap the bunnies between herself.
You're going to be in big trouble if you decide to write about relativistic quantum mechanics. She's going to have some really good ideas.
Yeah, it's a hard.
But Joanne, this Emmy's thing here, the way she doesn't quite catch on, apparently from reading Chad's physics books that have fallen onto the floor or something, is a misconception, a little off to the side misconception that most beginning physics students who are encountering relativity have trouble with too, in much the same sort of way. And it's that pesky problem that I think you talk about of, basically the guy with the pole running so fast, the pole's bigger than the barn, will he fit entirely inside or not? And that's a really tricky question, and it gets clearly answered. You did a great job with that. And I know from experience how tough that problem is.
Yeah, no, I've given that as an exam question when I teach our sophomore level class. A lot of what shows up as examples in the relativity book are adapted from the from teaching it at the sophomore level, where it's a ton of fun to do. But really weird stuff.
I read once, since we're on relativity for a moment, I read once that Einstein later on thought maybe relativity wasn't the word he would have liked to use, particularly since it didn't start out that way, and that I'd read some point that he said he would have preferred to use the word invariance. And I latched onto that thinking, invariance seems a really central idea, and you talk about the idea of invariance, but what do you think of that idea, and would it have changed the way you told the story instead of having to explain one word or one idea?
Yeah, there's a lot of these things. There's Werner Heisenberg also has a description of the uncertainty principle. Is called the uncertainty principle because Niels Bohr badgered him into using that particular word. But the word that he actually originally wanted to use was something closer to indeterminacy, which is much harder to say, but would sort of avoid some of the misconceptions. And relativity versus invariance is another of those kind of things. The neat thing about relativity is, in some sense, you can fit the entire theory on a T-shirt, and that the entire theory of relativity is the laws of physics do not depend on how you're moving, and everything comes from that. That the idea that that there are fundamental laws that are invariant depending on on your motion. They're completely independent of how you're moving. And everything comes from that. The fact that everybody needs to see the same speed of light you can see as sort of a consequence of that idea. And the fact that there shouldn't be any difference between feeling gravity versus feeling an acceleration in the opposite direction. That's another thing that comes out of this idea that fundamentally it's the laws of physics do not change depending on how you're moving. And that's really the key of the theory. And if it were called that would change some of the perspective that people have on it, certainly.
I was just going to say, do people tend to disbelieve you? Are they hard to convince when you say, no, really, the saying the speed of light has to be measured the same by everyone in an inertial frame is all of special relativity. Everything comes from that. I mean, that's remarkable, but I mean, who's going to believe that?
Yeah, it's an idea that that's the origin of the whole controversy to the theory. And people were thinking about this a long time before Einstein. The first ideas relating to relativity come from like the 1880s with people like Lorentz and Fitzgerald and the first versions of the Michelson-Morley experiment, where people are trying to see the change in the speed of light as you're moving due to your motion relative to the ether, and failing to find that. And that's a thing that caused a lot of controversy, and people had a lot of wacky ideas about how to fix that. And most of the math of relativity actually predates Einstein. Right? We call it the Lorentz transformation or the Lorentz-Fitzgerald transformation because all of the equations that you need were worked out years earlier, but people couldn't quite make it all fit together. And really, the beauty of Einstein's approach, and the reason he gets credit for special relativity, is that he made it clear that this is an inevitable consequence of a really basic idea, and you just have to think carefully about what does it mean to measure the time at which two events take place. What does it mean to measure the distance between two things? And if you think about those measurements and what you have to do to make those measurements, if you think about that stuff carefully enough, then you're inevitably led to the idea that moving objects shrink and that moving observers will disagree about what time it is. And everything else follows from that. And so those equations drop out of a really simple and powerful idea.
The historic progression is really a fascinating story too, of Maxwell's equations coming together and distilling into these four things, discovering that these equations imply that there's a wave of some sort involved because you can make a wave equation out of them, identifying that number in the equations, that constant, appears to be the speed of the waves, and it's very close to the speed of light, finding out that radio waves are very similar. In fact, they're the same as as light waves, discovering that the Maxwell equations are Lorentz invariant. That's an interesting mathematical feature until Einstein says, to avoid contradictions, let's go with this weird idea that the speed of light is constant no matter who's looking if they're traveling at a constant velocity. Wham! And suddenly here you have these Lorentz transformations that tell you that's why. And boy, a lot of crap, comes out of that. And then you get, for all the popular, you even get equals MC squared. Whoa!
Yeah. Yeah. So yeah, it's a really neat story, and to a large extent, the reason for Einstein's success is almost, it's not quite popularizing, because his writing is highly technical and has a lot of math in it, but it's extremely clear. The way he lays things out is very clear and compelling in a way that some more ad hoc treatments weren't, and people who were trying to hang on to the idea of an absolute frame somewhere had a lot of trouble making their ideas as compelling as Einstein was able to. And then that follows on into general relativity, which is really the part that's really original and unique to Einstein, is carrying that further to talk about acceleration and the relationship between acceleration and gravity, is just extending that same idea to a much a much more complicated scenario, and that is an incredibly powerful and very very successful theory.
So I have a, speaking of clear and being clear and clarity and in communication and all, so here's your book and you have some diagrams. Did anybody go, no diagrams? Don't, because we hear this over and over. Watch out your vocabulary. Oh, don't put that formula in there.
Equations.
How was this received on the publishing end? Because we
didn't have any problem with diagrams and pictures. There's a couple of places that I had equations and things, and that got some negative reaction. There's in the quantum book, there's one chapter where I had some equations, and I sent that one to a bunch of people who are not scientists, just as beta readers, and one of them wrote back that there was this set of equations on page 182, and it made me almost physically angry to have these equations there, that you expected me to know what that was. I actually ended up replacing those equations, or at least supplementing them with a picture, with a figure of showing a couple of different dogs and different scenarios of things that worked out. And so, yeah, the thing that ended up being a real shock and learning experience was in the first book. My editor for the first book was an English major, but read the proposal, really loved the idea, and bought the book. But we had a lot of arguments about jargon terms that didn't occur to me as jargon, and the one that always sticks in my mind is state. So, you have to define what do you mean state? What do you mean state of a particle? And my reaction was like, what do you mean? What do I mean state? It's the state. It's a thing. It's how do you not understand what that word means? And then stepping back a little bit, I'm like, okay, that is unclear, and so a lot of things are defined in that was really eye-opening in terms of what you need to define.
So
my writing process, as far as the editorial feedback goes, is always, I joke that I would get edits, comments from my editor, and I would spend 2 hours at dinner and after ranting to my wife about how this is absolutely outrageous, and how can they change my deathless prose like this, and this is ridiculous. I can't believe this is such a stupid thing. And And then the next day I would sit down and make the changes, and it's a much better book for all of the changes that I made.
For all the input. So from learning what people have given as feedback to you, especially people who are not physics-minded and maybe read the book, could you create a short list of what is it you wish people knew, like 3 things about physics you wish people would know and take to heart?
About physics specifically, there are some things, like I said, relativity you can boil down to a really simple idea that the laws of physics don't depend on how you're moving, and that's sort of a good thing to hang on to as an idea. It's kind of hard to beat the Feynman line about if civilization collapsed and you could pass only one sentence on to the post-apocalyptic wasteland, what would it be? And the idea is that everything is made of atoms, which are tiny little components of matter, and they stick together in larger ways. Because if you have that idea, if you know that that's true, then from verifying that idea, and you can work up in scale and you can work down in scale, and everything else can follow from that. And that's a really nice thing. More generally, I think what I'd like people to know more about, and the book that's in process now is about science more generally. Doesn't feature Emmy, but it's about science as a process, and the idea there is that scientists aren't doing anything mystical or magical. The thought processes that you use in making discoveries in science are things that we use every day. And there's a very simple process that's at the heart of doing science that consists of you look at the world around you and find something that you need to explain. You think about what might be a possible explanation for that. Then you test your explanation by making additional observations, by doing some experiments. And then you tell everybody you know what happened. Right? What was your idea? What happened when you did the test, and share those results. And that process is something that is extremely general and extremely useful in almost anything. And it's something that people use without realizing that they're doing it. But I think knowing that process of science, and that's the basis of science, and being aware of that is something that would be really powerful for people to know more widely.
What's the name of your book? What's the name of the book?
The name of the book is Eureka: Discovering Your Inner Scientist. It'll be out end of the year. I think at Amazon said December 9th. I currently have on the laptop that's just off screen here, I currently have the copy edits for that I'm going through.
Wow, we're that close. I got the impression from the way you introduced the idea that the physicist's idea of energy is something that you feel people misconstrue a lot. How hard is it to get them around to a physicist's view of energy?
Yeah, it's and that's one that I struggle with. I'm not sure I've been completely successful in the books at explaining what energy is. And it's one of these terms that's sort of been co-opted by a lot of nut jobs. So one of my great character failings is I'm a big fan of the TV show Ancient Aliens, because it's just ludicrous. It is completely ridiculous. But they're constantly talking about there must be some kind of energy field that's like, those words don't mean anything the way you use them.
Well, and you just answered a question I already had or begin. How about these things that have been adopted by so-called New Age groups? Things like taking Einstein's quantum spookiness that I think he regretted at some point, and saying, then this energy is transported across, and so this if this alien thing is making you nuts, then that surely must be driving you bananas.
Yeah, the alien stuff ends up being mostly it's where they do great violence to science is far enough. It's just far enough away from me to not upset, and it's sort of entertaining. They're talking about archaeology. There's people like, the last chapter of the quantum book. I call out a few people by name for doing just horrible quackery with quantum mechanics. Like Deepak Chopra has made this whole career out of this. You use quantum mechanics and Eastern mysticism, and if you meditate, you can measure yourself to be healthy, and then you'll live forever.
And you can create the universe.
Yeah, it's it's a bunch of crap. It doesn't work. If you could just by wanting things, there's the secret, right? If you want something badly enough and concentrate on it, you can make things come to you, and the universe will give you a bountiful wealth. And if quantum physics, if you could invoke quantum physics to make things come to you, we wouldn't have to write research grants. Right? The people who understand quantum physics would be able to money would fall from the sky, and that's not how it works. And so I find that stuff kind of maddening.
Yeah.
That's funny. Because as a biologist, so yeah, Jeff and I tend to set up our hangouts so it's one or the other. We either got the physicist side or the biology side. But so as a biologist, of course, I'm a cell biologist, and there are these people who say, yes, of course you can think yourself healthy, and somebody is trying to call in the middle of this. And it's really distracting me. You guys can't hear this.
Oh, yeah.
You can hear that?
A little bit, yeah.
Yeah, somebody's calling somehow. I don't know how they do that. But, okay, so now that they're gone and I can think a second here, that now they're sort of grabbing epigenetics, where something has happened, like whether it's been a famine or something, that this leaves an imprint on the DNA. So now, of course, they're saying, well, of course, if you think hard enough, that's going to leave an imprint on your DNA. And, of course, they invoke the all-magical quantum mechanics is doing this.
That's right.
It's actually structuring your DNA, but epigenetics is, so they're just grabbing terms that they don't fully understand. And so hopefully your Eureka book might shed some light for people on, you just don't take terms if you don't fully understand them.
Yeah, the hope is that getting people to have a little more of a sense of science as a process, and sort of that you can with a little bit of effort you can sort of trace out the steps, and even if you don't understand all the mathematical details, you can sort of follow. There's a chain of evidence that goes from here to here to here to here to here that gets you the thing that you're looking for, and that's a really powerful idea. Yeah, I should say though, there is a school of thought that says that the New Age people have done good things. There's a guy at MIT named David Kaiser who has a physics history book called "How the Hippies Saved Physics."
I saw that in the library. I didn't pick it up though.
It's a really good book, and he talks about how there was a big crash in the physics job market, kind of post Apollo. Where suddenly all these people who were getting physics degrees couldn't find jobs. And a group of them in California got really into counterculture stuff and sort of went back to the basics and rediscovered the cool, weird stuff about quantum mechanics that really got them excited about the idea and started looking at this philosophical implications and stuff. The particular slant they took was they were trying to use it to explain ESP and stuff like that. But they're poking at these ideas both through, sort of directly researching some of these questions, and also through apparently somehow annoying John Wheeler. Got research going on a lot of these foundational quantum issues again after decades where people just sort of swept that completely under the rug and didn't talk about it. They got that research going again, and that's really inspired a huge amount of physics and quantum information and quantum computing and teleportation and information transfer and that sort of thing. One of the stories is apparently somehow they annoyed John Wheeler, who then suggested to Bill Wooters and Wojciech Zurek that they should find a way to prove these guys wrong, and that led to the no cloning theorem, which is one of the fundamental things in quantum information. And from that, then you get a whole bunch of really interesting experiments that you can do, and that leads into ideas like quantum computation and things like that. So, so in an indirect way, really, the hippies did save physics. So,
I have a couple of quotations that I thought amusing enough to write down so that we could talk about them. One that I particularly like, I think you were talking to Emmy in one which book it was now, I'm not sure. I think it was in Relativity, and you said cartoons don't count as evidence. And I think that's a great thing to say, and it struck me as particularly interesting because I think not a lot of people confuse cartoons for reality. Why is that? Why don't we take that as how reality works? How do we understand that when we know that beginning physics students get a lot of details wrong about how gravity and other bits of reality work, but how can we tell that cartoons don't count as evidence?
Yeah, it's that's one of the sort of scare things from since I was a kid, right? People have always been talking about like, oh, these Looney Tunes cartoons, kids are going to be hitting each other with anvils, and I'm like, people are smarter than you think, and and they're not actually going to mistake the cartoon for reality at quite that level. So yeah, it's an interesting question how you can make things that are sort of quasi-realistic, but people don't quite fall for it. A number of the things that happen in cartoons, though, are sort of based on physics misconceptions, right? Mm-hmm. The Wile E. Coyote thing, where goes out halfway over the canyon and only falls after he realizes that he's there. That's one of when we teach classical mechanics, that's one of the misconceptions that people have, that if you launch a projectile, that it starts out going straight for a while and only starts to fall later. Yeah. And really the notion that it's falling the whole time, the instant it leaves the barrel of the gun, it's falling, is something that does throw people off a little bit. So a lot of what you see in the physics of cartoons ends up being based on sort of common misconceptions in some sense,
which makes it more recognizable to the viewers, no doubt. So almost familiar somehow.
Yeah. There's also possibly off that an analogy between some of the ways that we approach physics and cartoons, right? In that a lot of the models that we use are sort of cartoons of reality, right? When you're thinking about if you're thinking about states in an atom, right? Most of the time, the sort of image that we have in mind, if you're thinking about atomic spectroscopy, you're thinking about like a Bohr model sort of thing. You have an orbit and the electron moves out and then it's in a different orbit, and that's a really useful heuristic. But it's very much not what's happening, right? Really, you have at a somewhat more fundamental level, really, it's all solutions to the Schrodinger equation or the Dirac equation. Mm-hmm. You have a wave function that's changing. And if you go even more fundamental than that, if you're thinking about it in terms of QED, then you have an electron and it's exchanging photons with the nucleus, and you have to take into account all the virtual interactions and things like that. So most of the ways that we calculate things are actually on some level like a cartoon. In that it's an abstracted version of reality.
Yeah, and that ties in, oddly enough, with a couple of other things I'd written down, because I'm no big fan of the Copenhagen interpretation, which is a model, which is mistaken for part of the theory, if you will, of what it is, and it's not. It is a model. It is a cartoon for how things work. And in one place, I think you even talked about, I just wrote it down that way and didn't say which one of us we were thinking about. But the danger of the Copenhagen interpretation or any other model of physics is asking too much of it. It's an analogy, it's a cartoon, and sometimes useful, but it's not the theory. And then that merges with another question of, do we need an interpretation? Does quantum mechanics need an interpretation? Because it's really a way to describe experiments, measurements, and those sorts of things. And now that it's become confused with the interpretation.
Yeah, this is something that I've had a number of arguments on the blog. I go back and forth on my opinion of sort of philosophy and it's really foundational things. You know, at a deep level, I'm sort of a subscriber to the David Merman "shut up and calculate" interpretation, which is, you know, you can get the math and you can get the answers, and a lot of this philosophical stuff will come later. There are a lot of people, though, that a physicist named Matt Leifer, who posts comments on my blog somewhat regularly, makes a good point that you know, these different interpretations provide different ways of looking at some of these problems, and it can be very helpful to think about, okay, well, you know, if I wanted to describe this situation in this other language, sometimes that provides a way to look at things that is helpful. You know, gives you a clearer way of thinking about a particular problem, or, you know, may suggest a way to attack it. You know, at the moment, you know, we have these different interpretations of quantum physics because we have a very good apparatus for calculating numbers, you know, calculating what's going to happen, but we don't have a really good story to go with those numbers a lot of the time.
Right.
And so there's, you know, a feeling that there ought to be more to it. There ought to be something that, you know, you can explain at a deeper level. But for the moment, you know, all of the different interpretations give you exactly the same answers to every experiment that you can imagine doing. So, you know, there's a sense in which what we need is, there's this famous John Bell, is a physicist who's from Ireland, Northern Ireland, who, you know, there's this paper in 1935 where Einstein, Podolsky, and Rosen suggests that there's this spooky action at a distance phrase comes up, that, you know, you can have these long distance correlations between particles that seem to violate relativity in some sense, and it seems very troubling for quantum mechanics philosophically. Niels Bohr writes a response to this coming out of the Copenhagen interpretation that's basically, yeah, what are you going to do? You know, it says it with much more equivocation and you know, very complicated sentence structure, but it comes down to, that's just the way it is, and it sort of stays there for about 30 years, and it's in the mid-60s that Bell starts thinking about this really carefully and realize that you can actually do an experiment. If you think about what does it mean to have elements of reality of the sort that Einstein, Podolsky, and Rosen talk about, you can say that constrains the outcomes of experiments in a way that quantum mechanics doesn't. And you can look for a difference between those predictions. And then people, once he suggested that, then people went and looked for that difference and were able to find it and show that no, these quantum theories are really, really right. First, a guy named John Clauser in the 70s, and then the most famous set of experiments is by Alain Aspect, as a French physicist in the early 80s. So that's, you know, kind of an analogous situation. You had these two pictures. Einstein, Podolsky, and Rosen wanted there to be defined properties for things that we just hadn't figured out how to measure yet. Bohr said, no, things are completely undefined. And after 30 years of thinking about it, Bell showed that you could actually find a way to distinguish between them. In a sense, what we need for this question of foundational interpretations is somebody like that to eventually come up with, okay, here's an experiment you can do that, Copenhagen says this and many worlds says this. Go do the experiment and you'll see which one is right. But as yet, no one's come up with that kind of thing. And it's an open question as to whether it's possible to come up with that kind of thing.
I have a question here from someone who's watching, and is supposedly quoting Stephen Hawking, and I'm not sure if that's true or not, but it says, physics is a finished sentence. Do you agree with this statement? And supposedly that's actually said by Stephen Hawking.
Physics is a finished science?
Finished science, sorry, not sentence, science, right. Need to get bifocals.
I don't agree with that in the sense that there's still a lot out there that we don't understand. We don't know why it is that everything we see in the universe is made of matter and not antimatter. And we know that it is to a very high degree because we don't see any of the things that you would expect if there was an antimatter galaxy out there somewhere. You would expect certain things to be happening, and they're not. So since we don't see that, we know that everything is matter. But why that would be is not really understood. And we know a bit about the mechanism, but there's the standard model of particle physics can't explain the level of discrepancy that we see between matter and antimatter. That's why there's the whole question of what is dark matter. We still don't have any idea what that is. What is dark energy? We have even less idea what that is. What is why do neutrinos have mass? They really shouldn't. And it's sort of awkward you can just sort of stuff those into the standard model, but it's kind of awkward to do. So there's a lot of really fundamental questions that are still unanswered.
But
also, even beyond that, I would say there's a sense in which no science is ever over, because my training is in atomic, molecular, and optical physics. The central equations for AMO physics are mostly the Schrödinger equation, but you have some corrections that come from the Dirac equation, and then if you get really good, there's some corrections from QED. That's all nailed down by 1950, right? But in my field, 64 years later, people are still the field is thriving. I was at a big conference in the field a couple of weeks ago. There's just tons of exciting new things going on that come from taking these very well-known rules and applying them to new systems and more complicated interactions, and we develop new tools for looking at things. There's just this endless complexity of taking, there's no new physics showing up, but just taking well-known things and combining them in infinite possible ways will keep you going for years.
Yeah, I like the analogy of really science is like chasing marbles on the deck of a ship. There's always something to go after and something to, so I like to hold on to that one, because that's, what sort of keeps you in the lab and not go completely crazy. I do want to ask about one time I tweeted a photo from someone in the UK who found your book in the gardening section, and you said you found your book, the How to Teach Your Dog, in pet section. So what does this mean for science communication and reaching the general public?
Yeah, the ones that get me are I have a vanity search for my name, and so every now and then Google sends me updates saying we found your name, or the titles of the book. We found this someplace, and I keep finding these pirate sites, these places that are offering BitTorrent ebooks illicitly. And it's almost invariably sandwiched between like Cesar Millan books and these actual dog training books. And so I probably ought to be more upset about that than I am. But just the thought that someone is out there really wanting to teach quantum physics to their dog, just is highly amusing.
Or they're surprised when they pick up this book and realize this is not going to help me, get my dog to jump higher over,
Right.
In their agility runs or whatever, right?
But the other one, I've had people give me mediocre reviews on Amazon because the U.S. edition is just how to teach physics to your dog.
Right.
And I have like 3-star reviews on Amazon that are like, well, these explanations of quantum physics are really good, but it's only quantum physics. I'm like,
yes.
Like, you wanted what? Like, you want me to have an explanation of how your dog could build a trebuchet? Like, it's
how your dog can jump higher and
with a dog,
run faster.
I have one more quick quotation, Joanne, that needs your input too.
Oh.
Because I actually read Chad to write, "The business of science, particularly physics, is to provide a mathematical description of reality." Anyone want to comment?
Well, I will say, as a biologist, right, we're notorious for not just loving math. Like, my daughter loves 6-page math problems. She's a physics major. But I'm not totally averse to it. And what happened was, it was physics classes that made me love math, because I went, wow, I can explain anything, through an equation. Not everything, but, an equation often fits. And if you have all the pieces, things are defined, and then you'll realize, well, that factor has nothing to do with this, because that equation to that factor does not fit anywhere in here, no matter what you do. So to me, physics made math real and helpful, and I just gained a great appreciation from that practical application. But I'll let Chad.
Yeah, I didn't necessarily mean that in the sense of the, universe on a T-shirt, right? You want one equation, and it's the theory of everything that you can fit on your chest. But I think that ultimately science, and physics more so than some, is about making quantitative, testable predictions of things. Saying that we understand how this process works, and because of that, we can say that if you do this thing, the most likely outcome is this, and we can tell you with some certainty how likely that outcome will be, and tell you exactly what you should expect. Yeah. And
I think that's been its
they don't have to be elegant equation mathematical predictions, but you should be able to say something definite about, this will happen, this will not happen, and then you can go check that.
Yeah, that's surely several sciences' form of success, is being able to make those quantitative predictions. So that almost becomes what those sciences are.
There's a von Neumann quote that I use in the new book. That's something about how scientists, the real business of scientists isn't doing experiments or making measurements. It's that they construct models, and you come up with a model of how things work, and then that's what science is really about.
So will Emmy be making an appearance in any future books? Your next book, you say no, not your Eureka, but
Eureka, she's not in Eureka, except I think she gets mentioned in passing once or twice, but she's not a character in that. It's hard to come up with. Quantum and relativity are the big areas where a canine perspective, looking at the material from a different angle is really useful. It's hard to think of what the next thing to build a book around would be. So there are some odds and ends here and there, and she'll probably, now that I have to do copy edits, but now that the text of the next book is locked, you know, it's very possible that she'll make some more appearances on the blog. But you know, she's getting up there for a dog. She's about 12 years old.
Mm-hmm.
So getting into her respectable, you know, old age, and so she's happy to take it easy for the moment.
So speaking of Emmy, you and I think, and many other people know the truth that adopted pets make great friends. And I thought I think it was in the How to Teach Physics, at least, or in the version that I read, that you had a little shout out for where Emmy came from. So I wonder if let's do that, and if you could mention how Emmy came to live with you.
Yeah, Emmy's a shelter dog. We got her from the Mohawk Hudson Humane Society over near Troy, New York. It's about half an hour from here. And she was turned in by her previous owners because they got a puppy and then discovered that one of them was allergic. And so they turned her into the Humane Society. We went there and adopted her from there. And she's been just a fantastic dog. Really, really lucky. We got her. She was about a year old when we got her.
Wow.
She was already housebroken, so you know, fantastically convenient, and just she's a really sweet dog, particularly with people. Unfortunately doesn't like other dogs, and the one unfortunate thing for her in her old age is our next door neighbors moved, and the new people have a dog. The previous neighbors did not, and so that's going to be a source of stress for a little while.
For a little bit. No.
But I highly recommend, though, if you're looking for a dog, you know, you can find a lot of really fabulous dogs at your local shelter, you know, Humane Society organization, various rescue groups. You get some really great dogs that way, and they need somebody to take them in. So.
Yep. Well, Chad, thank you so much for joining us and for an interesting discussion that sort of went between dogs and, all different fields of physics. So we are really glad you are here, and we look forward to your new book so that we can all appreciate science and hopefully understand a little bit more how scientists think. Thanks to you, the audience, for joining us and those who submitted questions. Monday, I believe, we have our next episode, which we will be talking to the gentleman who wrote the book Marketing the Moon about selling the Apollo program to the general public. So if you'll join us then, we will be doing that. Chad, thank you. Any last words?
Well, thanks for having me, and you know. It's been fun, and you know, go out and do some science, everybody.
Thanks, Chad.
Remember to think like a dog when you're approaching the weirder parts of physics.
All right. Okay, everybody. Thank you so much.